Hello, this is Memphis Community University. Today we are doing some AP Calculus free response questions. And we are doing the topic BC multiple choice like, which actually isn't a topic, but there are always AP exam questions that can't be categorized and sort of the other topics like Taylor series or parametric or rate in, rate out, something like that. So we do have to sort it. These are the miscellaneous questions. And what we do is we go from difficulty 1 through 10. So we start off with easier questions that are sort of miscellaneous and then go up all the way up to difficulty 10. So sort of the harder questions that have appeared on the AP exam. And today we have a special treat. We are doing difficulty number 2. So still not too hard. But in this question, I believe that this is probably, this practice here that I have before you, this is based off a former AP question, which I believe to be the best written AP exam question. It's probably my favorite AP exam question. I am a weird little nerd, so I do have a favorite AP exam question, but it is hopefully, you'll see that it's aesthetically pleasing, if that can be described for a free response question, because what we're going to do is we're going to take this f of 2.8 number and we're going to approximate it in 4 very different ways. So that's why this is such a great free response question, in my opinion. Sort of this entire series is sort of based off this idea that watching from difficulty 1 through 10 should improve you not only for these free response questions that are miscellaneous, but also for multiple choice questions, because these are the multiple choice like questions of the AP, of the series that we have, of the videos we have. So basically, as you redo these 4 questions, hopefully they will not only help you with the free response questions, but also the multiple choice questions as well. So let's get started again. We have this table. Looks like we have one given f value and one given f double prime value at 2, and then f prime is in this table. I don't consider this a table free response question because table free response questions usually have some sort of situation going on, like particle motion or like temperature or something like that, temperature of some sort of thing or some rate in, rate out thing. So if you want to watch videos of those, we do have a series on that as well. So those are called table free response questions, and we go from difficulty 1 through 10 on those questions. So check that out if you want to practice those. But in this case, let's do this question. I am pretty excited to do this question because, again, I think this is a very well written free response question. So the first question is a AB level question. Same with the second question. The last 2 will be BC questions, Eulers and Taylor polynomials. But in this case, if you are taking AB, hopefully these first 2 questions will be useful for you. So equation of the tangent line is a very common question. So this is actually a tangent line approximation. So what we're going to do is we're going to cover up this 2.8 number, and we're just going to find the tangent line. In order to find the tangent line, what we need is we need a point and a slope. So I'm going to write the words point and slope, because every line, you can find the equation of the line using point slope form if you have a point and a slope. And then the word tangent, of course, means that our slope is going to be the derivative. So we just need the derivative will be slope. So it will be f prime of 2. Remember that we're not caring about this 2.8 number. We only care about 2, and we'll plug in 2.8 at the very end. So first we need to find the point, and here the point's pretty easy because it's right here, 2, 6. Finally, we want to find the derivative, so f prime of 2. Well, f prime of 2 will be in this table. We're going to be using this table in every single question. Looks like it's 5. Hopefully we can tell that's a 5. So now we are ready to write the equation of the line in point slope form. So it's going to be y minus 6 equals 5 times x minus 2. Y minus the y coordinate equals slope times x minus the x coordinate. So this is the equation of the line. This is how you do tangent lines for every single part of the AP exam if they appear. And then finally, we are doing tangent line approximation, so we are going to plug in 2.8 here into this function. So it's going to be y minus 6 equals 5 times 2.8 minus 2. Unfortunately, this is non-calculator, so we do have to do these decimals by hand, these multiplying and subtracting decimals. I actually like to use fractions better because I deal with fractions a little bit easier and I mess them up a little bit easier, and I'm trying to avoid mistakes as much as possible. So 2.8 minus 2 is 0.8, but that's the same thing as 80 over 100 or 4/5. So I'm going to write it like that. And of course, that's lovely because the 5s cancel automatically. So it looks like we're going to get 4 plus 6. So that means that y is equal to 4 plus 6, because these will cancel, and then you'll add the 6 over. So the approximation ends up being 10. So that's the first question. A nice little tangent line question to warm us up. All we did is we found point and slope, where slope is derivative, but none of this information was very hard to find because it was all given. And then finally we constructed the line, and then we plugged in our weird number at the very end to find the approximation. So again, what this free response question will be about is to approximate f of 2.8 in a variety of ways. The first one was tangent line question. The second one is a very important A, B, B, C topic. It's Riemann sums, and we're going to try to approximate f of 2.8 now. So the first thing that we need to do is we need to approximate this integral right here using a Riemann sum. You do want to know how to do all 4 types of Riemann sums. They appear equally often on the AP exam. Those are, of course, left Riemann sum, right Riemann sum, trapezoidal Riemann sum, and midpoint Riemann sum. The video series where we do table free response questions that I alluded to earlier, where every single one has a table, all of those, I believe, have Riemann sums if you want to practice those. But for now, let's do this one. So the key to remember about Riemann sums is that no matter which one you're doing, left, right, or trapezoidal or midpoint, it's always the difference in the x's times different y's. So in this case, we have 2 subintervals. So in midpoint, what we're doing is we're going to have one rectangle from here to here, and then one rectangle from here to here. And again, the thing I try to tell my students as much as possible is that when you take a rectangle, it's always the difference in the x's times different y's. So in this case, it's the difference in the x's, so it's 2.4 minus 2, and then it's going to be times different y's. So it's not going to be, if we were doing left, we would choose the left coordinate. If we were doing right, we would do the y value of the right coordinate. In this case, we're doing midpoint, so we're going to multiply by the function value of the midpoint. But it's always the difference in the x's. So 0.4 times either 5, or times either 11, or times either 7 in this case. So again, it's always the difference in the y's times certain x's. So in this case, it's going to be 0.4 times 7. So we're going to write 0.4 times 7. And then we take this guy, and again, it's always the difference in the x's times the different y's. So it's going to be 0.4 again, because 2.8 minus 2.4 is 0.4. That's the difference in the x's. And then we're going to choose to multiply by 12, because that's the the function value for the midpoint. If we were doing left, we would choose 11. If we were doing right, we would choose 14. But we're always difference in the x's times different y's. So in this case, we're going to get plus 0.4 times 12. Unfortunately, I do not have a calculator, so again, I'm going to employ the strategy of writing it as 4/5. Not 4/5. 0.4 is going to be 2/5. So that's going to be 2/5. Sort of like how 0.8 was 4/5, and that's double it. So times 7 plus 2/5 times 12. Looks like this is going to be 14/5 plus 24/5, which is going to be 38/5. Great. So 24 plus 14, 38. But remember, I do want to emphasize that sometimes, or a lot of times actually, especially in those table free response questions that I was referring to, the Riemann sum actually isn't the answer. The Riemann sum is used to approximate this integral right here. So we don't want to leave this as our answer. We have to do something further. A lot of times in these Riemann sum questions, what I tell my students is that the Riemann sum is not an answer. Usually you have to do an additional step. So and sometimes that would be like determining whether the Riemann sum was an overestimate or an underestimate. And that's based off increasing and left and right and stuff like that. Sometimes you're actually approximating the average of the integral. So you need to multiply this number by 1 over b minus a, because the formula for average is 1 over b minus a times the integral. And then here, we are trying to approximate f of 2.8. So what we have to do is we have to do the fundamental theorem of calculus. So I'm going to do that right here. So f of 2.8 is equal to, well, this fundamental theorem of calculus works always in the same way. We take our point 2 comma 6. So this is the y value, this is the given x value. I always put my given y value, I put my given x value on the bottom, I put 2.8, and then I put the derivative. And this is the fundamental theorem of calculus, one of the most important theorems of calculus, as its name implies. And for this integral, You set this up when you do particle motion for your response questions, when you do parametric for your response questions, when you have graph for your response questions, when you have accumulation for your response questions. So it does appear quite often on the AP exam. And when you do this integral, you have a variety of ways to do this integral, depending on the question. So for example, in particle motion questions, oftentimes it's a calculator. Sometimes in the multiple choice, you take an antiderivative if you know it. For graph response question, it's the area where you have to be careful with negative areas and flipping the integral. And then finally, for this one, we are not going to actually find the integral. We are going to approximate it using this Riemann sum. So 6 plus 38 over 5. We replace this integral with our approximation. So finally, we are going to find this add this number up, and we will be good to go. So 6 can be written as 30 over 5, of course, plus 38 over 5. So it looks like we are going to get 68 over 5. Hopefully you can tell that. You can write it as a decimal, but I'm not going to do so because I don't feel the need to. So the answer is 68 over 5 in this case. So let me just remind you of the two big things. The first thing is you have to know how to do all the Riemann sums. Left, right, trap, and mid. Riemann sums, in my opinion, are easy questions because you're only multiplying and adding things. You just need to know the correct thing to multiply and add. So it's always the difference in the x's times different y's, depending on if you're doing left, right, trap, or midpoint. Finally, remember that the Riemann sum is not always the answer because oftentimes you have to do an additional step with the Riemann sum approximation. In this case, we did fundamental theorem of calculus. What we did is we set up fundamental theorem of calculus in this way, which is the way I set it up every single time. Given y, given x, want x. And then to do this integral, there's a variety of different ways, but in this case, we used a Riemann sum, so we replaced our number with that, and then we added. So just keep in mind, know how to do all the Riemann sums. They can't really trick you with Riemann sum questions. If you know how to do the technique, you know how to do the technique. And then finally, just remember that Riemann sums are sometimes not the final answer, but you have to do one additional step. So in this case, we are done with that. This number, by the way, is probably around 65. 5 goes into 65. That's 13. So 13 plus 3/5, because there'd be a remainder of 3. So 3/5, that's 13.6. So it is around this number 10 if you wanted to actually write it as a decimal. But again, you don't have to do so. So now, those were the two AB topics. Tangent lines, of course, appear on AB topics. Riemann sums and fundamental theorem of calculus also appears on the AB exam. But we are now going to BC stuff. So BC stuff is Eulers and Taylor polynomials. Perhaps if you're watching this video in the future, Eulers method appeared on the AP exam, the AB exam, because that's the most likely thing to be added to the AB exam in the future. But for now, as of 2020, which is when this video is made, it is not on the AP exam for AB, only for BC. But Eulers method, if you know what Eulers method is, it's a pretty easy thing. I'm just going to write the general formula. It's basically, it's not basically, it is just the equation of a line. So what you do is, the formula is that I told my students, the new y you want is equal to the previous y plus the step size. And then you plug in the old x, let's say the previous x and the previous y, into your slope. So plug these two things into that. Oftentimes these appear on differential equation for response questions. We of course have videos on those where you're plugging in something for x and y. But in this case, it looks like because we have f prime values, we won't be plugging in any y's. But just be careful. Sometimes you do plug in x and y, especially in those differential equation for x. For example, our difficulty number 5 video of differential equations does have an Eulers method where you're plugging in both x's and y's. But in this case, we don't have to do that. This is Eulers method. It is just the equation of a line, because if you subtract this over, you would have y2 minus y1. Step size is actually the difference between the x's, x2 minus x1, because that's how much the x's are increasing. And then finally, this is just slope. So it is just the equation of the line. So let's do this right now. So I like to write out my original point, x is equal to 2. Again, the original point has to be given. It was 2, 6. we're doing two step sizes. So one problem that people do is they do Eulers too much. But the first one we are going to approximate is 2.4. And then the second one is going to be 2.8. So we're not going to do it 3 times. We're only going to do it 2 times. One from here, one from here. Usually Euler's method is 2 times. But you never know. So we're just going to apply this formula. So notice the step size between these two numbers is going to be 0.4. So we're going to have previous y, which is right here, 6, plus the step size, 0.4. Oftentimes the step size is written as an h. And then you're going to you can plug in the previous x and the previous y, so 2 and 6, into the derivative. But again, we have a chart of just f prime values, so we don't need to use the previous y, just the previous x in this case. And we're going to do f prime of 2. So it's just going to be f prime of 2. And f prime of 2 is 5, conveniently enough. So it's going to be 6 plus, going to change this to a decimal fraction, 2 over 5, times f prime of 2, which is 5. So they cancel out, which is nice. 5 over 5 is, of course, 1, so we get 8 here. And then we do the next step. We cover up the previous step, the original, and we're going to use this first line to find the second line. So remember, it's always the previous y. So in that case, it's 8 plus the step size. It's still the same step size throughout the question. Be wary that sometimes the step size is negative, but in this case, we're going from 2 and approximating 2.8. If you were going, for example, starting at 1 and approximating 0, the step size would be negative there. But in this case, it's positive. So it's 0.4. And then we're going to plug in previous x, previous y, which are these two, 2.4 and 8, into our slope. But again, that's just going to be f prime of 2.4. I do wish this number was 10, but unfortunately it's 11, but that's fine. So f prime of 2.4 in this table is 11. So we are done after we do some math. So it's going to be 8 plus something times 11. Again, 0.4 is 2/5. So this is not going to be the prettiest answer, but I don't really care. As long as I have a reduced form and proper integrals and proper fractions are perfectly fine. I don't need to change it to a decimal. I'm good to go. So 8, of course, is 40 over 5. Looks like 2 times 11 is 22 over 5. So you're going to be ending up with 62 over 5. 62 over 5, I think in decimals, is 12.4. And 12.4 is close to our other two numbers, which is pretty good. And so that is the answer. Euler's method, definitely not the worst thing in the world. Just be careful with it. Use the previous line to find each successive line. So for this line, we use previous x, previous y right here, and then previous x, previous y to find this one. If we had to do other steps, if we had to approximate, for example, the value at 3.2, again, we would use the previous x, which is going to be this, and the previous y, which is going to be this. So the line would read 62 over 5 plus 0.4, the step size, f prime of 2.8, which would be 14. But that's if you are approximating f of 3.2 for some reason. But it didn't ask me that, so I'm not going to do that. Hopefully you are good with Euler's method. Once you learn how to do it, you're good to go. But sometimes some students take a little while to learn it. But most of the time, once they learn it, they know how to use it, and they sort of don't forget it. Finally, of course, this is BC. Can't have a BC question without asking about Taylor polynomials. And in this case, this Taylor polynomial is actually a pretty easy question. We shouldn't be intimidated every single time we see Taylor series. Of course, Taylor series can be very hard. If you want to check out our videos on those on just Taylor series when we go from difficulty number 1 through 10, that's probably the hardest video series that I have, because Taylor series are the hardest for response question. But Taylor polynomials aren't too bad. So we have a Taylor polynomial at second degree, and then we are going, this is the center point, x is equal to 2. So let me write out the general formula for Taylor polynomial for you. So if any Taylor polynomial about x is equal to 2 looks of this form. It starts with f of 2 because that's the center point, f of a, plus derivative over 1 factorial. I like to write 1 factorial even though I know it's 1, because I like to write the form the same way. And then it's always x minus the center point to the 1. Finally, it's the second derivative at 2 over 2 factorial, x minus 2 squared. And this is the Taylor polynomial. Keep in mind that some people get confused with second degree Taylor polynomial and, for example, the first two non-zero terms. These two would be the first two non-zero terms, but the Taylor polynomial of second degree is a polynomial. So what you do is you include this, you go up to the square term and include everything before it. So just be wary that don't just find this term, you need to find the squared term and also the linear term and also the constant term. So if you were doing the third degree, for example, you would add one more term, the third term, but still include all of these terms. This is the Taylor polynomial. Remember that on each term, three things match. It's always the exponent, the derivative number at the point, and also the factorial. So in this case, for example, first derivative, 1 factorial, x minus 2 to the 1. And in all these parentheses, it's always x minus 2. Just keep in mind that the coefficient is not just the derivative, it's not just the factorial, it's the ratio of those two things. So again, this is the second degree Taylor polynomial for every single Taylor series about x is equal to 2. So we're almost done. All we're going to have to do is plug in some values for these numbers, and they were all given on the previous page, so it shouldn't be too bad. F of 2 was 6. F double prime of 2 was 12. So let's write that down first. So it's 6 plus something x minus 2 plus 12 over 2 factorial x minus 2 squared. And then finally, f prime of 2 is 5. So that's going to be 5 here. So again, this is the general formula for any Taylor polynomial, second degree, about x equals 2. And in this case, we found these three numbers, or we didn't actually find them. They were given to us. Finally, one last time, we are going to approximate 2.8 using this Taylor polynomial. So what we're going to do is we're going to plug in 2.8 into this function. It's going to get a little bit messy, but I feel like I'm confident that we can do it together. So again, when you plug in 2.8 minus 2, you get 0.8. I like to write it as a decimal. I'm going to write it as 4/5. Then 2 factorial is nice because it's just 2 times 1. 12 times 2, 12 over 2 is 6. And then finally, we're going to have 4/5 squared because, again, when you plug in 2.8, you do square it. So this might get a little bit nasty, but I believe in us. So this part right here is pretty good because when you cross out this 5 and 5, you get 10. And then it looks like we're going to get 6 times, well, when you square a quotient, you have to square both the numerator and the denominator. So this is not going to be the hardest fraction to combine because 10 is a nice number. It's 250 over, it's not 250, yeah, it is, sorry, I don't know what I'm saying. To write 10 with a common denominator of 25, I'm struggling towards the end, but that often happens in these videos. It's going to be 250 over 25, because obviously if you cancel out the 25s, you end up getting 10. Then you have to do 16 times 6. I don't really know that off the top of my head. I do know 16 times 2, that's 32, and then I need to triple that. So 32, 64, 96, I believe. And then finally, 250 plus 96 shouldn't be too bad. It's 250 plus 100 minus 4. So that's going to be 350 minus 4 is 346. And is this number close to the other numbers? Well, this is around, well, 25 goes to 100, obviously 4 times. So it's going to be 4 times another 4 times another 4 because it's 300 times basically 2 more. So it's around 4, 8, 12, 13, 14, which is around this number. So it seems like it is a legitimate answer. I'm not going to change it to a fraction because I want to be done with this. But again, hopefully you see that when they just strictly ask about Taylor polynomials, the questions actually aren't that bad. Just form the Taylor polynomial first, write the general formula. This is how I like to do it because I don't like to go straight to the formula for the specific function because I want to write it out and then just plug in numbers. It's just easier to plug in numbers when you can see it on your page as opposed to doing it in your head. But hopefully you had as much fun on this free response question as I did. I do think that this frick is the best, was well-written, simple frick because it covered such a variety of topics. Again, that's going to be hopefully the goal of this entire video series. As we go from difficulty 1 through 10, you will see a variety of BC topics where some of them are also on the AP exam. So what we did in this question is we did tan line approximation. That was the easiest question. Point and slope, where slope is derivative, and then we plugged in 2.8 to approximate 2.8. We did a Riemann sum question where we first found the Riemann sum with a midpoint because it was asked to do midpoint, always the difference in the x's times the y value of the midpoint. But we remembered that the Riemann sum is not actually the answer. We had to do fundamental theorem of calculus where the Riemann sum is the approximation of the integral. So this is the setup of the fundamental theorem of calculus. Given x value, given y value, want x value. Finally, we did some BC stuff, but the BC stuff actually wasn't very bad. We did Eulers Method, where Eulers Method is this sort of algorithm. To find the new y, you take the previous y, the y in the previous step, and then multiply the step size with the previous x, previous y, into whatever your slope formula is, f prime in this case, sometimes dy dx, and other Fourier response questions. So we did it twice. Use this step, use this line to find this, use this line to find this, using this formula right here. Finally, Taylor polynomial, again, just write the general formula, start pulling in numbers that you know, f of 2, f prime of 2, f double prime of 2, they have to be given in some way. And then once you find the Taylor polynomial, which is this guy right here, you can label it T2 if you want, or second degree Taylor polynomial, every single term up to and including the term where the power is 2. This is the approximation, so T2 of 2.8. And then we just found it. So hopefully this was useful. Again, continue watching this video series. I'm sure that it'll be a lovely review as you take the AP exam, and if you want to just review topics on what you've learned throughout your calculus journey. But I hope that it continues a little bit further, and I will be there with you. Thanks again for watching.